Alright, this section is antiderivatives and indefinite integrals. We're going to just start with the definition of an antiderivative. So we spent a lot of time just working on derivatives, and today we're going to do the inverse of that and look at the antiderivative. So the definition is there: a function capital F is an antiderivative of f on an interval I if capital F prime of x is equal to the original function for all x in I. So let's look at a couple examples of that. Previously, and we've been working on derivatives, so if I gave you some function here and I said, what is the derivative of x squared, then you would say the derivative of that is 2x. And that's pretty easy. We've been doing that. What about this function, the gx function, x squared plus 17? Well, the derivative of that is still just 2x. And then we look at the h of x function, capital H of x, and we look at this and we take the derivative of that, which is 2x again. So we can see that f of x is equal to 2x, and any antiderivative of that has the form x squared plus some constant, because here it didn't matter, that one didn't have a constant, this one had some constant, and this one had a different one, but it doesn't matter because when you take the derivative of that, that part goes to 0. So if you know the derivative of a function, the process for finding the original function is called integration, and the function is called the antiderivative. So when we look at this notation, it's the integral of f of x dx is equal to capital F of x plus a constant, because remember there's some constant there. And c is just an arbitrary constant, and it denotes the family of all antiderivatives of f of x on that interval. So up here it was the family of all of those. So more specific notation here is we see that that's our integral sign. The f of x portion is called the integrand. D of x is the variable of integration. And over to the right, we have the capital C is just the constant of integration. And like I said, we make the notation that denote that integration is the inverse of differentiation and vice versa. So we'll use those properties as we go throughout some to work those. Now, some common indefinite integrals, and if you want, go ahead and pause the video at this point and jot these down, but the integral of 0 is just a constant. The integral of k is kx plus c. These are some of the main ones that you use, but this is probably by far the one we use most often. So it's just x to the n plus 1 over n plus 1 plus a constant. N cannot equal -1 because, of course, that would make our function undefined. And then, let me go back up one. This we do a good bit too. This coefficient can just be pulled out front, and we'll do that a lot. Anytime you see a coefficient, you can pull it out in front of the integral sign. And then, of course, you got your trig function, sine, cosine, secant squared, cosecant squared x, secant x, tangent x, and cosecant x, cotangent x. So those are just some trig functions. Like I said, take a few minutes, pause the video so you can jot these down. These are just your formulas for your basic indefinite integrals. Alright, so we're going to move on. I'm just going to work a few examples with you here, just so you can kind of get the gist of what we're going to be doing. So the first thing, just like we would do in derivatives, when we're looking for the antiderivative, if we can algebraically simplify and make things a little bit easier, we can do that as well. So we're going to rewrite here as the integral of, when you multiply like bases, add the exponent, so you'll have x to the 8th dx. Now this one fits the format, and I'll write this formula for this one on the previous page, was x to the n dx is equal to x to the n plus 1 over n plus 1 plus some constant under the condition that n cannot equal -1. So this is, like I said, this is the most common one we use. So here we're going to take that, using this formula, we'll have x to the n plus 1. So in this case, our n is 8, so n plus 1 over n plus 1. And that's just going to simplify to x to the 9th divided by 9. And then this is the thing we got to remember, plus some constant. So that's the antiderivative there. And so once we start doing this a lot more, we won't necessarily have to write down all the steps in this part because you'll get very familiar with it. But just for the beginning one, we'll write that down so you can see the use of that formula to the right. Okay, let's look at the next one, number 2. We have, we want to rewrite. Let me get we want to rewrite because we can rewrite this using a negative exponent. X to the negative 3 dx, and then now we want to take the antiderivative of that. So to the n plus 1, so x, let me write this one out this time again, to the n plus 1 over n plus 1 plus a constant. So we'll simplify that, and that's just going to be x to the negative 2 over negative 2, and of course that's plus a constant. I can do that at the end. Let me rewrite that. So I'm going to have a negative. I'm bring it's a negative. I have a 2 in the bottom, and I'm going to bring my x squared down. So let me put 1 as a placeholder. So simplified, and then my plus a constant. Or you could have left it x to the negative 2 over a negative x to the negative 2 over 2 plus a constant. All right. We'll look at one more of these here. Let's rewrite this one as well. If you can rewrite using exponents, that's going to probably be your best because this particular integration rule is using an exponent. So if I rewrite this one, it's going to be x to the, this is a 3, so it's going to be 2/3 power dx, and now we're going to do x to the n plus 1 over n plus 1. So 2/3 plus 1, which would be 3/3, would just give us 5/3, and then when you do this, it's going to be divided by 5/3, but this is an easy transfer here when you simplify that because you would multiply by the reciprocal, which is 3 over 5, so you're just going to get 3/5 x to the 5/3 plus a constant. And you'll become very fluid in going from this step to this step without having to do all the calculation. Because like I said right there, if you need to see the scratch work on it, multiply by the reciprocal, which is 3 over 5. So multiply by the reciprocal up here, which is 3 over 5. So that's how that looks. But you can kind of do that without all the extra work as we move through more of these.